before I start, I would like to have a copy of the presentation of Professor Jahan also, if it's possible. But okay.
I'm sorry I didn't get that.
Okay, good. The topic I will talk to you now is my PhD research that I did between 2017 and 2020 in Mexico City, more concretely in National Autonomous University in Mexico. Now I'm doing a postdoctoral research in Staff Merida, near all the Mayan Zone, Mexico. And let's start. The motivation of this work was the perovskite structure. As you may know, the perovskite structure is paradigmatic in material science since it is involved with piezoelectric, superconductivity, and ferroelectric phenomena, for example. And currently, there is a race for solar cells based on the perovskite structure. And this race coincides with machine learning applications, which have proven to be faster than conventional quantum chemical calculations. In order to prove new chemical compounds with the perovskite structure, we built a machine learning classifier to identify crystal structures. This machine learning classifier was built using compounds reported as synthesized and were taken from crystallography open database. After training the machine learning classifier, we used it to assess the probability of proposed compounds to adopt a crystal structure, more concretely, the perovskite structure in the qubit symmetry, with the characteristic vertex shared octahedral framework. Now I will give you some details behind the construction of the machine learning classifier. This machine learning classifier was based on artificial neural networks. One of the most important things to take into account when you develop a machine learning classifier is the characterization of the samples, that is the materials. By characterization, I mean how we describe the materials to let the machine learning classifier to distinguish among different crystal structures. Crystals are systems having long-range order in their particles. Due to this long-range order, there is periodicity. And as a consequence of this periodicity, you can identify a minimal cell known as a unit cell. This unit cell reconstructs the whole crystal after application of translational operations. And thus, the description of a crystal simplifies from 10 to the power of 23 particles to only those atoms within the unit cell. In crystallography, a crystal is defined as a combination of a lattice of points and a basis. In real three-dimensional space, there are only 14 different possible lattices. These lattices are known as the Bravais lattices. And the basis is a set of atoms that we use to decorate the points of the lattice. All the information of a crystal compound is found in a crystal information file, also known as CIF. And in a CIF, you can find information about the space symmetry group, the lattice parameters of the crystal, and the center of the lattice points. And the most important information that you can find in a CIF file is the location of the atoms in the unit cell. More concretely, the atoms in the basis. Here in the slide, I show you the atoms of the barium titanium oxide in the qubit perovskite structure. The basis contains 5 atoms, but in the CIF, you can see that there are only 3 atoms, one for the barium, one for the titanium, and only one of the 3 oxygen atoms. This is because the 3 oxygen atoms share the same neighborhood of atoms. Basically, they see the same neighborhood of atoms. And in crystallography, those atoms having the same chemical neighborhood share the same point symmetry group. There is another way to say this, and this point symmetry group corresponds to Wyckoff sites. Wyckoff sites gather positions in real space with the same point symmetry group. And instead of describing the 3 oxygen atoms, you only need to describe one of them, since the other 2 atoms basically see the same neighborhood. In real space, the atoms located in site belonging to a point symmetry group, the Wyckoff sites gather those sites within the same orbit, to be more specific, the same orbit of a point symmetry group. And the occupation of these Wyckoff sites define the typical polyhedral framework that characterizes a crystal structure. For example, in perovskite structure, the characteristic polyhedral framework is a octahedra. In blend or wurtzite, we can identify tetrahedra, and more examples that are in literature. The typical polyhedral framework may preserve even when there is a symmetry lowering of the crystal, as happens in the perovskite compounds with a vertex-shared octahedral framework. The most popular picture of a perovskite structure is the one corresponding to the cubic symmetry, but there are perovskite compounds with orthorhombic symmetry, monoclinic symmetry, and even with triclinic symmetry. So the approach taken in my PhD research was to consider the different chemical environments of the crystal compounds to construct a set of features. This is a simplification of the characterization in terms of the number of atoms within the unit cell. As I told you, you can describe the crystals with the atoms of the unit cell, but now I'm proposing you that we can describe these crystals with the different chemical environments within the unit cell. And this is the reason behind the name of this kind of artificial neural networks, which are based of crystal site. And this set of features, we use this set of features to fit an artificial neural network that will classify compounds in terms of the crystal structures. In order to characterize the compounds, we use a set of structural features and chemical environment features. The structural features were geometrical factors and packing factors. The geometrical factors are essentially quotients between atomic grading. And as you may know, there is a geometry around a central atom associated to the value of a quotient. Depending on the value of the quotient, you can have a tetrahedral geometry around the central atom or a cubic geometry around the central atom, and so on. For example, if you have a collection of compounds with up to 4 Wyckoff sites or 4 different chemical environments in the crystal, there are 6 different quotients which corresponds to the geometrical factors, and these quotients are found with the number of combination formula. And similarly, this is not shown in the slide, but if you have a collection of compounds with up to 6 Wyckoff sites, the number of geometrical factors that can be calculated with the number of combination formula is 15. Now, the packing factors are basically quotients of sum of pair atoms. And one of the most important packing factors is the Goldschmidt tolerance factor. The Goldschmidt tolerance factor is conceived for the perovskite structure after assuming that there is close packing of hard sphere atoms. Again, in a collection of compounds with up to 4 Wyckoff sites, you can initially obtain 6 combination of atom pairs for doing addition, 6 different sums. And with these 6 different sums, you can make 15 different combinations to create packing factors. as it is shown now in the slide. In a collection with up to 6 Wyckoff sites that is not shown currently in the slide, with this strategy, you can obtain 105 packing factors. And now I mention a collection of 6 Wyckoff sites because it is the results I will show you later. Now, the features describing the chemical environment refer to the neighborhood within a certain cutoff radius, depending on the occupied crystallographical sites by the atoms. In the slide, I show you the 4 neighborhoods around the 4 crystallographic sites in the calcium titanium oxide with the orthorhombic symmetry. The titanium atom locates in sites with the 4A Wyckoff site. Similarly, calcium locates in sites with 4C Wyckoff site. And in calcium titanium oxide with the orthorhombic symmetry, there are 2 types of oxygen. Since the oxygen occupy 2 kind of crystallographic sites, one labeled as AT and another one labeled as 4C. And sorry. And we can distinguish the neighbor atoms depending on the crystallographic site that they occupy. In the slide, I show you the neighborhood of the calcium located in 4C sites, and we can split the neighbor atoms according to the sites that they occupy. For example, the titanium atoms occupy 4A Wyckoff site, and something similar happens with the oxygen that occupy sites labeled as AT and 4C. The way that we model this chemical environment is with local functions that have a Gaussian profile, as shown in the formula. Those neighbor atoms closer to the central atom have a larger contribution to the value of the local function. And this interaction between the central atom and the neighbor atom is modulated by the sum of the atomic radii of the involved atoms. In a collection of compounds with up to 4 Wyckoff sites, there are 12 local functions or 12 features describing 12 chemical environments. And in a collection with up to 6 Wyckoff sites, you can obtain with this formula 30 local functions. And after you compute all these features, structural features, which are packing factors and geometrical factors, you concatenate them to make an input vector useful for your artificial neural network. And with this info, the artificial neural network is able to differentiate among the crystal structures. Now, I will show you some results obtained with this methodology to construct the features. And the results now that I show you are published in this article, which has the same name as the current talk. And in the article, a set of artificial neural network were constructed, but I will only mention you one of these artificial neural network. This artificial neural network was developed with up to 8,000 compounds. And these compounds were described with up to 6 different chemical environments or Wyckoff sites. And this gave place to 163 features. The compounds were classified by the artificial neural network in up to 10 different crystal structures. And after training the artificial neural network, we used the structured features by the hidden layers to establish a linear correlation with the lattice parameters of compounds having the structure of garnet, espinels, perovskite in the cubed symmetry, orthorhombic, and rhombohedric, as well as in rootless and popper structure. And the lowest correlation coefficient that we got after establishing this linear correlation was 0.95. Now, the target crystal structures of this artificial neural network were those shown in the current slide: garnet, espinel, layered perovskite. With layered perovskite, I mean Dion-Jacobson and rootless and popper structures, fluoride, perovskite, alite, hexagonal perovskite, this other variant of the perovskite structure, and ilmenite. And by perovskite structure, I mean the one related to the vertex share octahedral framework. In an hexagonal perovskite, as you may know, the octahedral framework is created by phase sharing. In the table, you can find the results after training validation, that is optimizing the artificial neural network, and in the test set, which are compounds completely different than those used in the optimization process. The average precision after the compounds in the test set was 91%. And the lower precisions that you can find in the table are ascribed to a scarce number of compounds having the structures. For example, there are only 7 compounds in the test set with the ilmenite structures and 11 compounds with the OTP perovskite structure. And some low scores are also explainable since there are a low number of features describing some crystal structures. For example, in the fluoride and alite structure, there are only 2 different chemical environments, which yield to give place to a low number of features. Well, as I told you, the purpose behind making these classifiers was to find candidate compounds to adopt the perovskite structure. And in this work, we used an artificial neural network to assess the probability of a proposed compound to adopt the perovskite structure. This artificial neural network was trained with compounds. Well, the one with the results I'm showing you now, the artificial neural network was trained with compounds with up to 4 Wyckoff sites and was trained to only distinguish compounds having the perovskite structure and those that do not have this kind of structure. The compounds found as feasible as candidate by the artificial neural network were validated with EFT calculations using the PV-SOL. And the compounds that preserved the perovskite structure were published in the article that is shown in the slide with the assessed band gap. Now, I must tell you that PV-SOL is good to estimate structural parameters, but tends to underestimate the band gap. Nevertheless, it can shed some light about the trends in the periodic table. And the compounds that you can find in the article shown in the current slide were allied. Another question that we had is if it's possible to use extracted features by the artificial neural network, by the trained artificial neural network to estimate band gap of a material. If so, the artificial neural network can be used to find compounds with a certain crystal structure alongside with the band gap. And basically, we tailor these compounds by selecting some atoms and proposing a structure. And recently, we have used the extracted features by one of the trained artificial neural networks to create an input vector useful for a convolutional neural network to assess the band gap. And we used the values reported by Kim and co-workers in 2020, which are band gaps calculated with an hybrid functional, the excuse area functional, which is supposed to be better than PV or generalized grading approach functionals. This work has not been published, but we obtained a mean absolute error of 0.55 electron volts with compounds of the training set, that is during optimization. And in the test set, we obtained a mean absolute error of 0.72 electron volts. Below, you can find the number of compounds against the difference between the band gap calculated by Kim and coworkers and the band gap predicted by the convolutional neural network. And the important thing here is that with the compounds of the test set, the absolute error, well, the 75% of the assessments done by the convolutional neural network had an absolute error below 1 electron volt. And we can say something similar. There are 95% of the assessment had an absolute error below 2 electron volts. The important thing here is to make this error lower in order to have more accurate predictions. But it is important to mention that these results can be improved and were obtained with an artificial neural network, with extracted features from an artificial neural network, whose task was different to classification. Now we are doing regression, and the features that we are using were features of an artificial neural network that was developed for classification, not regression. Either way, the feature construction around crystallographic sites are consequent with our knowledge about crystal chemistry. And conclusions, well, crystal site artificial neural network have proven high precision in the classification of crystal compounds. And we have to keep in mind that these artificial neural network are functions to prove in a faster way new chemical compounds. And the structured features by this artificial neural network are suitable to establish correlation with properties such as band gaps and lattice parameters, as I mentioned to you. Well, I would like to thank to National Council of Science and Technology for the PhD scholarship, and to the Artificial Intelligence Laboratory of Institute of Physics of UNAM, where I did my PhD. And if you want to contact me, you can send me an email to gomezperalta.ai Gmail, and you can find me in the website, in this website. And thank you for listening to me.